At the risk of a general rebellion, I'm going to go back to the realm of differential relationships and show you a few more that involve thermodynamics. I want to stress again that these differential relationships allow us to uncover certain truths about the relationships between different thermodynamic quantities without actually knowing the equations that they belong to, without knowing the functions that they represent. So let's dig in. I'll remind you that for the 256th time in this class, I'm going to write down the first law relationship, but now we're going to use this more elite way of expressing the differential using this expression TdS minus PdV. And I'll also specify that this is a reversible process. I can't have the equal sign there if it's not, because I know that this dq is going to be less than TdS if it's not a reversible process. All right, but now I can use this essentially as the starting point for writing similar things down for both the Helmholtz energy and the Gibbs energy. So let's start with the Helmholtz energy. So I might write the Helmholtz energy as U minus Ts. And when I do so, that means I can write dA is equal to d of U minus Ts, or d of U minus S dt minus T ds. But I have the expression for U given up here, so the TdS part is going to cancel, and I'll end up with a differential that looks like this. Oops, minus PdV. So in essence, without doing very much work at all, I can already derive an expression for the total differential of my Helmholtz energy. And in doing so, I end up expressing it in terms of temperature and volume. And it turns out these represent something we're going to call the natural variables for the Helmholtz energy. Okay, the natural variables are just the ones that that provide us with maybe the simplest expression for the exact differential. We can express the Helmholtz energy in terms of other thermodynamic properties as well, but this is the one that's going to prove to be the most powerful. If we always start with the first law expression or this version of it, we will get to expressions that will give us these quantities in their natural variables. Okay, now I'm going to do the same thing for the Gibbs energy. And the Gibbs energy, you may recall, is equal to U plus PV minus TS. So now when I write out the total differential for the Gibbs energy, I'll end up with du minus S dt minus TdS, just as I did up here, but plus PdV plus VdP. All right, a lot of stuff to add up here, but we can already see that this thing is going to cancel with one of the elements of this, and this thing is going to cancel with the other element of that. So I'm going to be left with an expression that says that dg is equal to S dt plus V dP. And again, we recognize now that temperature and pressure end up being the natural variables for the Gibbs energy. I should have specified what they are here in the Helmholtz energy, but they are temperature and volume. Okay, unsurprisingly, we derived the Gibbs energy when we were looking at processes that involve constant temperature and constant pressure. Now, I want to use these as a starting point to talk about some other special differential relationships that we're going to be interested in. So, for example, if I want to write the total differential of A as a natural function of temperature and volume, and this is just going to use the prescription that we learned a while back for how to write down the exact differential or the total differential for a function like this. It would be the derivative with respect to t at constant volume, dt, plus the partial derivative at constant volume, of volume at constant temperature, dv. All right, so all I've done is to write down an expression for the exact differential, or the total differential, of this function Helmholtz energy that's written as a function of temperature and volume. Now I could do the same thing for the Gibbs energy, but written as a function of temperature and pressure. And if I do that, Again, following the prescription, I'll have the partial of G with respect to T at constant pressure, dt, and the partial of G with respect to pressure at constant T, dP. All right, so now what does this tell us? Well, I can compare these two expressions with the ones that I have just derived up here. So for example, for Helmholtz energy, I got minus S dt plus PD minus P dV. So I got minus S dt minus P dV. So what that tells me is that I can associate minus S with this partial derivative. So that tells me right away that this partial derivative, dA dt at constant V, is equal to minus S. And similarly, the partial derivative of A with respect to V at constant T is minus P. I better put a semicolon in there to separate these two. All right, this is useful information because both entropy and pressure, as we've discussed, are properties, physical properties of the system. They both are positive, or I should say they're non-negative, which means that both of these derivatives, since they have a minus sign in front, these both indicate that A decreases with increasing temperature and volume, with increasing temperature and volume. All right, so it's information that we have now about the Helmholtz energy that we may not have had before, but by analyzing these total differentials, we get that information. Now, what about for the Gibbs energy? Well, I have my expression up here for what it is, and it's minus S dt plus V dP. So this tells us now that I can write down the following partial derivatives, or identify the following partial derivatives, that dg dt p is just equal to minus S. And similarly, dg dP at constant temperature is just equal to the volume. Okay, in the case of the Gibbs energy, what we find that's interesting, I suppose, is that as a function of temperature, we would expect G to decrease as the temperature increases because its derivative is negative. We would also expect, as a function of pressure, we would expect G to increase because its derivative over here is a positive number. All right, it turns out that these are really interesting pieces of information that are going to help us a lot when we start looking at phase transitions. So already we're going to get some payoff, if you will, from doing this differential analysis. So I hope when you see these things, I know that they can be a little bit difficult to digest. You may feel like I'm going to ask you to memorize these things. That is not the case. You can always look up these relationships if you need to. What I want you to do is to see these relationships and be able to deduce these kinds of conclusions from the results that you see.